very recent work that I've been working on with Dr. Mark Wilde at LSU in the Quantum Science and Technologies group. So it's exactly what it says on the tin. This is algorithms that we developed to test a Hamiltonian for symmetries under some group. So to start off with, I'm just going to try to motivate why we care about this. Why is this important to the grander scheme of physics? And then how does symmetry fit in quantum computing? And then after I hopefully convince y'all that it's an important question to ask and an important thing to consider, I'm going to take you through the roadmap of how we approach developing this test. Me personally, I'm not a big fan of presenting proofs. So the entire second half of this talk is really just going to be walking you through the logic of how we move from one step to the other. So let's start off with Noether's theorem. So Noether's theorem famously relates conserved quantities with symmetries in your system. And it is, without hyperbole, one of the most important theorems in physics. I mean, Noether's one of my favorite mathematicians. It's just an amazingly profound theorem that beautifully encapsulates why do physicists care about symmetry. So Noether's first theorem says that whenever you have a system dominated by a Hamiltonian, then any symmetric transformation that is conserved in the Hamiltonian corresponds directly with conserved quantity. And so this gives us our famous, most important relationships in physics. You're talking energy conservation. So if my Hamiltonian is symmetric with respect to time, my experiment works the same way tomorrow as it did today, then energy is conserved. And similarly, if you have it such that it is symmetric with respect to spatial translations, or equivalently moving from one inertial frame to the next, then momentum is conserved. And this underlies all the physics you've done since kindergarten, right? They always start you off with these conservation laws, and Noether's theorem is at the heart of it and really sets the stage for the importance of physics, of symmetry in physics. And this applies in classical physics and quantum physics. There's even Noether's theorem for quantum field theory. So it's really baked into every aspect of physics. But in quantum mechanics, if you're looking for a symmetry with respect to your Hamiltonian, it's always phrased in the way that you have some operator like we have here, some Hamiltonian that describes the dynamics of the system of interest. And then we say that there's a conservation happening, or there's a symmetry if our operator commutes with our Hamiltonian. So the next step to that is often considering not just one operator, but a group of operators. And that is what we see in the next one, where you consider, all right, now I have some group and I want to see if my Hamiltonian is symmetric under the action group. Well, it looks like the exact same thing, except instead of just one operator, we require that every representation of our group elements commutes with the Hamiltonian. So, what's a practical example of when we expect things to work like this? If you think of the group SO3, and we use this to describe rotations in our system, for instance, you can think of the hydrogen atom, where you imagine something that's spherically symmetric, and you say, oh, it's symmetric under all rotations, and we say that every representation of SO3 commutes with our Hamiltonian, and that gives rise to our rotational symmetry and describes our angular momentum conservation. Okay, so that's symmetry in physics in general, and you can imagine that if something's incredibly important to physics in general, then quantum computing would also be concerned with it. So let's talk about how symmetry is encapsulated in quantum computing in specific. So there's some groundwork already laid here. Particularly, there's a sort of common framework that is established when discussing these sort of symmetries in a way that quantum information and quantum computing people care about. So typically we consider discrete finite groups with a unitary representation, and this just means that it's a group that we have a way to put on a quantum computer, right? It's easy to put unitaries on a quantum computer. And then we further restrict ourselves typically to projective unitary representations. So that just means like you mod out by the identity. And it kind of encapsulates the fact that global phases are unphysical on quantum computing. We can't really tell the difference between them. So we would prefer that we not include unitaries that differ only by a sign, for example. And you furthermore will often want to restrict to a faithful representation, just meaning that like the transformation between your group and your representation is 1-to-1. And both of those together are really just meant to prevent trivial representations. You can imagine you can take a group and send out every element to the identity, and that's a pretty boring representation. So the next thing to consider is, what do I mean when I say symmetry in quantum computing? Well, there are two quantities that you would really care about. There's symmetry with respect to a state and symmetry with respect to a quantum channel. So I'm sorry, I heard a chat go off. Is that Zoom chat? I can't tell if Zoom chat's going off.
No, there's nothing in the chat.
Okay, cool. All right, I'll just continue on then. Yeah, so you care about symmetry with respect to a state or symmetry with respect to a quantum channel. So just in case you're not familiar with what a quantum channel is, you can essentially think of it as a trace preserving map that takes one quantum state in a Hilbert space to a different quantum state, potentially in a different Hilbert space. And unitary channels are literally formed by conjugation of unitary, as you see here. So what makes a state symmetric? It's whenever you can take the action of a group on a state, and the state is invariant under the action of those group elements for all of the group elements in your group. Okay, that makes sense. Invariant symmetry, as you do. But when we talk about symmetry of a channel, we typically talk instead about the covariance of the channel, which is to say that the action of the unitary channel commutes with the action of the channel that you claim is symmetric. So what does that mean? So say I have some unitary representation, as I have here, and then I have my two labs, one for Alice and one for Bob, and they have some channel that sends states between them. And each member of the lab has a way to implement the unitary representation. And if Alice acting with the group in her lab and then sending the state to Bob is completely equivalent to sending the state to Bob and then he acts with the group element, then we say that the action of the group commutes with the channel, and we say the channel is covariant. Now, big caution, step back. In all of the literature on this subject, and throughout this talk, you're going to hear symmetric with respect to a group. I'm going to say that, and that's really what's written. But in reality, it's symmetric with respect to the representation. These tests are going to be highly dependent on the representation of your group that you're using, and they will not, in general, be unique. They will not be irreproducible. They will not be irreducible. So it really is symmetric with respect to a particular choice of unitary representation. However, in the literature, they typically just say symmetric with respect to a group. And I'm a physicist, so I'm going to continue the tradition of abusing that notation, but just keep it in your mind whenever we say, oh, with respect to this group, it's really with respect to the unitary representation you're associating to that group. All right. So that being said, I'm never going to mention that again, and I'm just going to keep saying group. All right. So what problems of interest can we address by finding the symmetries of a Hamiltonian? Well, first, for a quantum information theoretic sense, you might be curious about the resource theory of asymmetry, which there's a lot of literature on if you're interested in that. But basically, symmetry can indicate resources, or rather lack thereof. In the resource theory of asymmetry, typically the symmetric states are not the resource states, the one that break the symmetry. And Iman Marvian has a lovely work expanding on Noether's theorem in the context of quantum mechanics, where he discusses this. Symmetry can also indicate superselection rules. So again, if you have like an atom in your mind and you're thinking about transitions in the atom, some transitions never happen because they're forbidden, and symmetry is what guides those selection rules. Basically, you're not allowed to make a transition that breaks the symmetry shown in your Hamiltonian. And furthermore, you can improve the performance of quantum variational algorithms. So, as we all, first time we learn Hamiltonians, we learn, for every particle, you have like 3 degrees of freedom, unless you can identify a symmetry, and each symmetry you identified gets rid of a degree of freedom, right? It restricts your problem, makes it easier for you to calculate. Same thing goes whenever you're talking about like computer programs looking at a Hamiltonian. So you can imagine if you have a quantum variational algorithm that has like these many degrees of freedoms to care about and these many states to optimize over, whatever the case may be, that symmetries will restrict that and make the calculation easier and thus improve the performance. Okay, so now I've hopefully motivated one of the most like widely appreciated concepts in physics, widely appreciated in both math and physics actually. And now we can talk about what we're actually doing, which is our approach to testing Hamiltonian symmetry on a quantum computer. So here's sort of the roadmap that I'm going to take you down. So if you don't follow any individual step, this is the basic idea of what we were doing. We said, all right, well, we have a Hamiltonian and we want to put it on a quantum computer. How do you do that? Well, you take its dynamics and you make them into a quantum channel. And that's something you can put on a quantum computer. And now I said before that symmetry of a channel, we call that covariance of the quantum channel. And there's a way to test for covariance Hamiltonian dynamics. I'm going to give that to you. And then I'm going to say, wait, hold on, I can simplify this. And there's going to be some manipulations going on there. And then I'm going to take the acceptance probability of this algorithm and look for that commutator relationship. When I see commutator, I'm going to think symmetry. When I can get that to appear directly in my acceptance probability, I'm going to celebrate. And that is a necessary part of the algorithm, 100% required. So how do you realize Hamiltonian dynamics on a quantum computer? Well, first you take a Hamiltonian and exponentiate it. And obviously you set h bar equal to 1 because theorist units. And at this point, it's up to something called Hamiltonian simulation. There's a lot of literature on how to simulate a Hamiltonian on a quantum computer. That's not really the point of our work, but there are some popular choices that are easy for us to adopt. For example, we use Trotter-Suzuki method whenever it comes time for us to put something on a quantum computer. And if need be, I can go over that in detail, but essentially it just assumes that your Hamiltonian is K local, so it only works on, some amount of qubits, some small amount of qubits, and then you can approximate it as like a product of Hamiltonian dynamics with some error, and the error goes away for small enough time, or if all of these operators commute. So essentially, the whole point of this slide is just to say, I can have a Hamiltonian and then put it on a quantum computer. First step done. The next thing that I need to do is I need to,
Probably show your slide on Trotter-Suzuki because not everyone is in quantum computing.
Right. I had it already. It's a process called Trotterization. And just to draw it out really quickly to illustrate what Mark's talking about, if you have some Hilbert spaces that are like designated by these different lines, and you have some global Hamiltonian that looks like that, Trotterization basically allows you to say, well, the Hamiltonian is composed of some local Hamiltonians that I can write as like a product, something like this. So imagine all of these are exponentiated. So maybe this one is on these two. Sorry for my poor drawing skills, ... what have you, where this would be like K equals 2 local. So K is basically, you can think of it as number of qubits it's acting on. And then you can approximate the action of your entire Hamiltonian via a product of dynamics of the local Hamiltonians, and you have some error associated with that. So it's typical if you do Trotterization, to take time to be very small to make that error go away. Or alternatively, if you have a local Hamiltonian where everything commutes, like you can imagine if you have something that looks like this. Well, these two commute, so characterization error is going to disappear. Again, this is just like a popular method to emulate a Hamiltonian on a quantum computer, and it's one that we adopt whenever it comes time for us to actually like test our algorithms. And feel free to ask me more about this later if this was unclear. Okay, so that being said, I have turned my Hamiltonian into a quantum channel, which is basically just a unitary in my circuit at this point. Now I need a way to test for covariance. Well, it is a known result that you can do this using something called the choice state of the channel. So what is the choice state of a channel? Basically, you take a maximally entangled state, think Bell state, you take 1/2 of the state and send it through your channel, and 1/2 goes through a reference system. And that's what I've drawn for you here, except this is a schematic for some general channel, and I have now developed a unitary channel of my own, given a Hamiltonian, so I'm going to get rid of that N and replace it with my Hamiltonian dynamics, and this will create the choice state of the dynamics that I am interested in. Given the choice state of a channel, I can now do a covariance test. So what we do is first we define our control register. So our control register is going to be in something we call the plus state, where it's an equal superposition over a set of basis states where each state corresponds to a group element. So you can imagine some orthonormal set, and then you label them in some consistent way where each one corresponds to like one of the basis elements. And then you define a projector where you act on one of the systems with your unitary representation, and on the other system with the complex conjugate of the unitary representation. And this obeys all the rules of a projector. It is equal to its own square, and this is mildly important if you want to check some acceptance probability results of ours on the next slide. So given this plus state and this projector, and then additionally this condition on the choice state, which is to say that a channel is covariant if and only if its choice state is invariant under the action of this projector, like so. So I have a choice state associated to my Hamiltonian, and I have this lovely property and also the control state that I have designated. And so I can make a pretty simple test to test for the covariance, and this will do that. So you take your maximally entangled state, which is bipartite, you make your choice state by sending it through the channel first, and then you act with these controlled gates, controlled unitary gates, controlled off of your plus state, where that initial construction where your basis states corresponded to a group element just means that when this is in the G state, it triggers U of G on these systems, right? So the probability of this to be accepted is equivalent to testing for this statement here, and that's where you're going to need the projector is equal to its squared property. To see that, you can just replace this with pi of G squared and use the cyclic property of the trace, pull it around, and you will see exactly equivalent to testing for the property that we wanted. So this is a covariance test of our Hamiltonian dynamics. But now comes the time to make this simpler. So if you're familiar with tensor networks, you might realize that this picture of an entangled state makes what's called a cup. And if you have something called a cup, you can do something called the transpose trick. This is also mathematically rigorous, but it's easy to see in the case of tensor diagrams. And you just kind of scoot your gate down to the other side of the cup. And this is all mathematically rigorous except for one thing, and it's called the transpose trick for a reason. You have to add a transpose to your gate. And that being said, this is a conjugate transpose, and on good days, that's a Hermitian conjugate. So you end up with something that looks like this now. And we can further simplify this by just noticing that nothing is happening now on our reference register. And so we can effectively trace it out. And if you trace out half of a maximally entangled state, what you get in the end is a maximally mixed state, which is indicated here by identity over D, where D is the dimension of your state. And then going through this and calculating the acceptance probability of this test exactly, you get this lovely equation, which you can convince yourself just by algebra and manipulation is exactly equivalent to this result here. And if you're not convinced, feel free to read our paper and we'll convince you. So now you have this, and this is nice and lovely, but it's not quite obvious that this relates to symmetry. I want that commutator relationship, right, that I always think of when I think of classical quantum mechanical symmetry. So what can I do? Well, I can notice that there are some exponents in here, some e to the IHT, and I can Taylor expand that. I'm allowed to do that assuming this condition holds. This quantity we call tau. I already said t is less than 1, and it's pretty normal to get the operator norm of your Hamiltonian equal to 1, or you can renormalize it. And so that's all fair, and I'm allowed to Taylor expand this, especially because we're in finite dimensions. So I'm pretty sure you can also do it in infinite dimensions, but you have to be a little bit more ashamed of yourself when you do that. So you Taylor expand this, and then you use cyclicity of the trace and linearity of the trace. And this fun fact that I have here, which just relates the absolute value of the common commutator with something that looks like what I have here if you were to, I don't know, Taylor expand it. And you can substitute that in, and after sufficient algebra, you will see that you get this lovely simplification where to the first non-vanishing order in T, when you do this, just as an aside, when you go through the algebra, you'll notice that all the odd terms vanish, which is just a nice little caveat. But when you go to first non-vanishing order in T, which is typically what we care about when we Taylor expand a quantity, you'll see that your acceptance probability for your previous algorithm goes as 1 unless the commutator of your unitary representation and your H is non-zero. So let me rephrase that just a little bit, because this is the commutation relationship that I noticed before when I was talking about what do you look for with symmetry given Noether's theorem. And this is to say your acceptance probability will be equal to 1 if and only if every group element commutes with the Hamiltonian. This is our symmetry relationship, exactly as you would want it to appear, given the typical form of it in quantum mechanics. And we actually call this quantity, when you add the 1 over d, the normalized group commutator. I'm trying to write that out, but my handwriting is atrocious, and I apologize. So we have a way now in this rather simple algorithm to estimate the normalized group commutator efficiently. And so now we celebrate because that's indicative of symmetry. But maybe you had a problem with the fact that we concatenated it. You know, we stopped at the first order in T, and you're like, what is the exact acceptance probability to higher orders? Well, we figured that out as well. So again, we're still using the Taylor expansion, but when you keep all of your terms, it can simplify to this form, where this is the nested commutator, where basically you have like something that looks like this. Commutator, commutator, HU, where this is nested in fold. And so this nested commutator gives you all your higher orders. And you can see very clearly that if it commutes for one order, it'll commute for all of them. And so in the case that you have a Hamiltonian that's symmetric with respect to your group, once again, you'll only get the n equals 0 term, and your acceptance probability will be exactly equal to 1. So this is great. This is the celebration time. But maybe you had a different problem. Maybe you have a problem Now with the fact that there's this 1 over d here, and that's a bit of an eyesore for you. So what happens if you want a result that doesn't depend on dimension? Because that's not pretty. Sorry, I got ahead of myself. I'll come back to that. So what you can do instead is you can say, well, I can optimize over every input state. I'm not going to put in the maximally mixed state because that gives me the dimension of 1 over d. I'm going to instead put in a pure state, and specifically the best pure state that I possibly can. So I'm going to maximize over all of the pure states that I can put in. And when you do something like that, that is essentially a quantum variational algorithm. And so the way you model this for like complexity theoretic approaches is you consider that you have some prover, which is indicated here by P, who has infinite computational resources, and so can always pick the best pure state to go in. And you get an acceptance probability that depends on the twirl of your operator, where the twirl is basically this quantity here. So we call this the twirl. And you get the infinity norm of your twirl because you're optimizing over all of the potential input states you put in. And we see, again, through Taylor expanding and substitution and some algebra, we see that this is also going to be bounded by the nested commutator that we saw before. So once again, we get an acceptance probability that is highly dependent on symmetries. Exactly, you would recognize it from quantum mechanics, although now we've introduced a prover, and this is a variational algorithm, so it's just a little bit less efficient to do. But pleasantly, there's no dependence on dimension here. So going back, I told you we have all of these relationships between symmetry and acceptance probability. Now you might say, okay, well, can you do this on a quantum computer? And so we took a simple toy example and put it on a quantum computer to see what symmetry tests look like on current hardware. So I found this Hamiltonian is the weakly J-coupled NMR Hamiltonian. So it is relevant in physics, although it is very simple. And you can easily observe that this has a Z2 cross Z2 symmetry when your representation is I tensor I tensor Z, Z tensor I, and Z tensor Z, right? So that makes sense. This is a simultaneously diagonal representation. This is diagonal. We expect that this Hamiltonian would exhibit this symmetry, and sure enough, when I simulate it, I get that it's the acceptance probability for our algorithm is equal to 1 for all time. Great, fantastic. What about on a real quantum computer? Well, I took a NISQ quantum computer, specifically IBM Lagos, and I took a bunch of runs on various different times. And as you can imagine, because it is very noisy right now, it's not exactly equal to 1, and I honestly wouldn't expect it to be. But it is very high degree of symmetry, as we see here, and pretty steady, and it doesn't decay away. All right, well, so that's a test of symmetry on our Hamiltonian. What about something that we don't expect to be symmetric? Well, I 100% do not expect this to exhibit dihedral symmetry. So I take D3, and you can make a representation of D3 by combining C0 and swap gates. And it's a fun homework problem if you just want to like sit down and convince yourself that that is a representation of D3. These are not the rotation and flip respectively. They just generate the group. And you would not expect this to be symmetric with respect to this group, and sure enough, it's not. When we simulate this, and I actually simulated this for much larger time than I'm displaying here, you have a very low degree of symmetry, and then if you actually zoom out, the amount of runs I was able to get on the real computer was obviously much fewer than those I can simulate, but if you zoom out, you'll see that it actually goes asymptotically to 0. I would draw that for you, but I've proven I have many things, but not an artist. So we have some real runs that we can compare to. We can say, we're more indicative of symmetry, we're less, and so on. we've related it to a quantum variational algorithm. And now I get to give you my going away point, which is essentially that we have developed two symmetry tests, one of which is an efficient algorithm to compute the normalized commutator between a Hamiltonian and a group. Another that uses a variational algorithm that is independent of dimension. But the big takeaway message I want you to have on our work is that for both of these algorithms, the familiar symmetry relationship from quantum mechanics appears in the acceptance probability of both algorithms. So if you have a good guess for a type of symmetry that your Hamiltonian would exhibit, we can test for it. And it is very clear the connection between our acceptance probability and the quantity you care about. And then this leads to interesting future directions for work where obviously the next step is to learn the symmetries. I have a way to test for them. Now is there a way, given a Hamiltonian, I can look for symmetries that Hamiltonian exhibits and try to find ones that are not trivial, and that could help reduce the complexity of your problems. So with all of that being said, thank you very much for listening to me. I really appreciate giving this talk and having this opportunity. References.
All right, let's thank Margarite for speaking to us. Does anybody have any questions?
I have one question.
Okay.
So I was wondering if you could elaborate a little bit more on how you could use C0 and swap gates to turn a representation into a dihedral symmetry.
So, sure. So I believe so if you write out a dihedral group, it is generated by rotation and flip such that rotation cubed is equal to identity is equal to flip. And then you have this restriction, right? Oh, that's the wrong number. That, right? So that's your dihedral group on their triangular dihedral group, correct? So I believe I chose, try not to mess this up, R equal to C0 and F equal to C0 swap. The easiest way to picture this is actually with the circuit diagrams for me, because you have, this is C0, and then swap is this, right? Okay, so this is C0, this is swap. And so your group elements become C0 swap, which is this. This is RF, or no, not RF. This is C0 swap. This is F. Okay. Swap C0 is actually equal to C0 swap, C0 swap. So you get this guy. So this is, I said this was F. Yeah, I messed these up. This is F, this is R. So this is R squared. And then if you were to do it again, you can see that R cubed would end up with identity. And then the only one remaining is RF, which is C0 swap C0. So that would give you this element. And you can convince yourself that that forms the whole dihedral group.
All right, thank you so much.
No problem. Any other questions?
I think, George, you're muted.
Okay, sorry. And I can ask also something. Thank you for your talk. Thank you for your nice talk. So you want to examine whether the Hamiltonian has symmetries. You don't know whether or not it has, right? So you do this, and the formula depends on all commutators. I saw that the formula that you had there depends on all commutators of higher order of the Hamiltonian, not only of the first order, right?
Well, so let me erase all of these things. So the leading order in time. So one, remember that the constraint we put on time is that time is less than 1. So as you go higher in order in T, it contributes less and less. And so leading order in T depends only on the first commutator.
But this expression is legitimate for all T, right?
Yeah, so this one is, it is legitimate for all T, but it's dominated by the leading order in T.
I see.
Especially in the regime where T is less than 1. That's my point. It's still valid, but it's dominated by this order.
I see. Sometimes also another question is, sometimes people check whether for the digital quantum simulation, what is the complexity of the simulation? But here, I guess, since you don't know the Hamiltonian, you don't ask this kind of questions in this work, right?
Right. We can say that we are limited by the representation and the Hamiltonian. So if you assume that your Hamiltonian is efficiently realizable, and you assume that your unitary representation is efficiently realizable, then our scheme is efficiently realizable for the normalized commutator. But the complexity could come in on either of those fronts. You could have a really terrible to emulate unitary representation or a really terrible Hamiltonian.
I see. Thank you.
You're welcome.
Are there any other questions?
Maybe I'll just comment some future things that we're thinking of. Like a natural question is how to do this for continuous symmetries.
Right, yeah.
That's something we'd like to do for compact groups. Maybe there's something clever that can be done. Or potentially use continuous variable quantum computers, right?
Right. Yeah, that's one of the things that we've discussed doing as a follow-up is continuous variable, or there was a work on putting representations of Lie groups on a quantum computer by basically discretizing them. And yeah, and as you just add more and more representatives, you get closer and closer to a true representation of the group. But the paper was very, very abstract on how you would actually go about doing this in a meaningful way.
Oh, okay.
Yeah, so.
Did we talk about that paper yet?
Mhm.
We did? All right.
Mhm.
Okay.
Anybody else?
All right. Well, thank you everyone for tuning in and listening to our work and giving Margarite this opportunity.
Yeah, thank you for speaking with us.
Yeah. All right.